Welcome back to Signal 2030, where we explore the scientific breakthroughs shaping our future. In Part 1, we explored the science behind fusion, the physics of ignition, the triple product, and why this challenge has captivated scientists for decades. Part 2 explored the magnetic path, where powerful fields are used to confine and control plasma in machines like tokamaks and stellarators. And now, in Part 3, we turn to a radically different approach, one that relies not on containment, but on speed, compression, and the power of light. This is the world of inertial confinement fusion, or ICF.
In stark contrast to the quasi-steady, patient approach of magnetic confinement, ICF is fundamentally a pulsed method. The goal is to create fusion conditions through a violent, extremely rapid, transient compression of a tiny fuel target, typically a few millimeters in diameter, a small spherical shell containing a layer of frozen deuterium-tritium fuel.
And you compress the sphere. How?
The core idea is to satisfy that Lawson criterion, NTT, by achieving extraordinarily high densities, the N, for an extremely short period of time. This relies on an external energy source, what we call the driver, usually banks of powerful lasers, though particle beams are also considered to rapidly deposit a massive amount of energy onto the surface of that tiny DT fuel target.
Lasers zapping a tiny ball? Okay, how does that compress it?
There are two main ways to use the lasers, two main drive mechanisms. The conceptually simpler one is direct drive. Here, the laser beams are aimed directly and as symmetrically as possible onto the surface of the fuel capsule itself.
Makes sense. Direct hit.
The intense laser energy rapidly heats the outer layer of the capsule, turning it into an exploding plasma. By Newton's third law for every action, there's an equal and opposite reaction. This outward explosion of the surface material drives the remaining inner portion of the capsule inward, compressing it like a tiny spherical rocket imploding on itself.
Okay. What's the downside?
Direct drive is theoretically more energy efficient because the laser energy goes straight to the capsule. However, it demands an incredibly high degree of illumination uniformity. All the laser beams have to hit the target perfectly evenly all around. Any slight imbalance can seed instabilities that wreck the implosion.
Tricky. What's the alternative?
The alternative is indirect drive. This is the approach used by the world's largest laser facility, the National Ignition Facility, NIF, in the US, where they achieved ignition. In indirect drive, the laser beams aren't aimed directly at the fuel capsule.
Where do they go then?
They're aimed instead at the inner walls of a small, hollow cylinder, usually made of a high atomic number material like gold or depleted uranium. This cylinder is called a hohlraum. It's German for hollow cavity.
Hohlraum.
The lasers heat the inner walls of the hohlraum to extremely high temperatures, millions of degrees. These hot walls then radiate a flood of soft X-rays. The fuel capsule sits inside the hohlraum, and it's this bath of X-rays coming from all directions off the walls that ablates the capsule's surface and drives the implosion.
So lasers make X-rays, and X-rays drive the implosion. Why?
The key advantage is that the X-ray bath inside the hohlraum is naturally much more uniform and symmetric than trying to aim dozens or hundreds of laser beams directly at the tiny capsule. It smooths out imperfections in the laser illumination.
Better symmetry. What's the catch this time?
The catch is efficiency. You lose energy in the conversion process from laser light to X-rays, and then from X-rays to ablation pressure. So, indirect drive requires significantly more laser energy to achieve the same implosion conditions compared to direct drive, assuming you could get perfect uniformity with direct drive.
Trade-offs again. Okay, let's unpack the implosion itself. You said it's like a 4-act play.
That's a good way to visualize it. It happens incredibly fast. We're talking nanoseconds. But there are distinct phases. Act 1, energy coupling and acceleration. The driver energy, whether direct laser light or indirect X-rays, is absorbed by the capsule's outer layer, the ablator. This material heats up rapidly, turns into plasma, and explodes outward. This ablation pressure acts like rocket exhaust, accelerating the remaining cold, dense fuel shell inward at tremendous velocities, often exceeding 300 kilometers per second.
300 kilometers. That's insanely fast. Okay, Act 2.
Act 2, deceleration. As the shell converges towards the center, it starts compressing the low-density DT gas that was initially trapped inside the sphere. This gas heats up as it's compressed, and as pressure starts to rise dramatically, pushing back against the imploding shell. This pushback causes the shell to decelerate rapidly.
Hitting the brakes. Act 3.
Act 3, stagnation and hotspot formation. The implosion momentarily comes to a halt. That's stagnation. At this point, the enormous inward kinetic energy of the shell has been converted primarily into the thermal energy of that central gas region. This creates a small, extremely hot, over 100 million Kelvin, but relatively low-density central region known as the hotspot. Crucially, this hotspot is surrounded by the main fuel mass, which is now much colder but has been compressed to incredibly high density.
They're a hot, low-density core surrounded by cold, super-dense fuel. And Act 4.
Act 4. Ignition and burn propagation. If the conditions in that hotspot, its temperature, density, and size reach the threshold for fusion ignition, DT reactions start occurring rapidly within it. The alpha particles produced by these initial fusion reactions are trapped within the hotspot and by the surrounding dense fuel due to the extremely high density. Remember, density helps trap alphas.
The internal fire kicks in.
Exactly. These trapped alphas deposit their energy right back into the hotspot and, crucially, into the surrounding, slightly cooler, dense fuel layer. This rapidly heats the adjacent cold fuel up to fusion temperatures. This triggers a thermonuclear burn wave that propagates rapidly outward from the central hotspot, consuming the rest of the dense fuel in a chain reaction. This releases a massive burst of fusion energy, far exceeding the driver energy, before the whole target disassembles hydrodynamically.
Wow, when it works, it really works. But you called ICF a precision nightmare. Why?
Because achieving that perfect spherical implosion needed for efficient hotspot formation and burn propagation is unbelievably difficult. The single greatest challenge in ICF is controlling hydrodynamic instabilities.
Instabilities again. Different from the tokamak ones.
Very different. These aren't magnetic instabilities. They're fluid dynamics instabilities that occur during the implosion itself. Any tiny imperfections on the target surface or any slight non-uniformity in the drive pressure can grow catastrophically during the acceleration and deceleration phases.
How do they grow?
The most critical one is the Rayleigh-Taylor instability. This occurs whenever a heavier fluid is being accelerated by a lighter fluid. In ICF, you have the heavy, cold fuel shell being pushed inward, accelerated, by the lighter, low-density plasma that's being ablated off the surface.
Heavy push by light. That sounds unstable.
It is. Any tiny ripples or bumps at the interface between the shell and the ablating plasma will grow exponentially. These can grow into spikes of the cold, dense shell material penetrating right into the forming hotspot, cooling it down and preventing ignition. Or they can grow into bubbles of hot, low-density material rising up and potentially rupturing the shell, letting the fuel escape before it's fully compressed.
So tiny flaws become catastrophic failures.
Precisely. There's also the Richtmyer-Meshkov instability, which occurs when a shock wave passes through an interface between materials of different densities, causing perturbations to grow. Controlling these hydrodynamic instabilities requires incredibly smooth targets and extremely uniform drive pressures. It's a constant battle against physics trying to tear the implosion apart.
And it's not just the fluid dynamics. You mentioned laser issues, too.
Right. Beyond the hydro instabilities, ICF also has to contend with laser plasma instabilities, or LPIs. These occur as the intense laser beams propagate through the plasma corona that surrounds the capsule. The high-intensity light can interact with the plasma in undesirable ways.
Like what?
Several things. Instabilities like stimulated Brillouin scattering, SBS, and stimulated Raman scattering, SRS, can scatter the laser light away from the target or reflect it back towards the laser optics, reducing the energy coupled to the capsule. Worse, these processes can generate high-energy hot electrons.
Hot electrons sound good, but they're not.
Not in this context. These hot electrons are too energetic to be stopped in the ablator. They can fly ahead and penetrate deep into the cold fuel shell, preheating it before it gets compressed.
Why is preheating bad?
Because if the fuel is preheated, it becomes stiffer and harder to compress to the extreme densities needed for ignition. It's like trying to squeeze a balloon that's already partially inflated versus one that's empty. You need the fuel to stay as cold and compressible as possible until the final moments of stagnation. LPIs and the hot electrons they generate work directly against that. There are other LPIs too, like cross-beam energy transfer, CBT, where energy can be parasitically transferred between different laser beams in the plasma, upsetting the drive symmetry. It's a whole zoo of complex interactions.
Okay, precision nightmare indeed. And then there's the target itself. You said it's tiny, but critical. The unsung hero, or maybe villain?
Absolute critical. We talk a lot about the lasers and the physics, but target fabrication is often overlooked, and it's a monumental challenge in its own right. These targets, typically about 2 millimeters in diameter, are not just simple spheres. They're complex, multi-layered structures. Often a plastic or beryllium ablator on the outside, then a layer of solid, cryogenic DT ice, and possibly gas in the center.
And they have to be perfect.
As close to perfect as humanly possible. The layers must have incredibly uniform thickness. The surfaces, especially the inner surface of the DT ice layer, must be atomically smooth roughness measured in nanometers. Any bumps or imperfections can see those devastating hydrodynamic instabilities we talked about. They are truly marvels of microengineering.
But that sounds expensive and slow to make.
Exactly. And that's the crux of the problem for turning ICF into a power source. For a commercial power plant, you'd need to perform these implosions repeatedly, maybe 5 to 10 times per second. That means you'd need to mass produce millions of these incredibly precise, complex targets every single day.
Millions a day.
And they'd have to be incredibly cheap, probably costing only a few cents each to be economical.
A few cents. What do they cost now?
Currently, these high-precision targets for experiments like NIF are painstakingly fabricated, often largely by hand or in very small batches using specialized techniques. Estimates vary, but they can cost hundreds of thousands of dollars each. And facilities like NIF, being research machines, are designed for high precision, not high repetition rate. They can typically only perform about one shot, one implosion per day.
From millions per day at cents each to one per day at hundreds of thousands each. That's a huge gap.
It's a staggering gap. The sheer scale-up required in target manufacturing technology and cost reduction is one of the biggest hurdles facing ICF energy.
So despite that huge gap, there has been a major breakthrough recently, right? At NEF?
Yes, absolutely. And it was truly a landmark achievement for the entire fusion field. In December 2022, and several times since, the National Ignition Facility, NI, achieved what's called scientific break-even. For the first time ever in a controlled fusion experiment, the energy released from the fusion reactions in the target, about 3.15 megajoules in the first instance, exceeded the laser energy delivered to the target, which was 2.05 megajoules.
More energy out than in? Q greater than 1?
Q scientific greater than 1, yes. Specifically Q target 1. This was a monumental validation of the fundamental physics principles of ICF that scientists have been working toward for decades. It proved that achieving ignition and propagating burn in a laboratory setting is possible.
That's fantastic news. So problem solved.
So, yes and no. The NIF achievement was monumental scientifically. It proved the physics works. But, as we just discussed, it also casts a very stark light on the immense systems engineering challenges that lie ahead for ICF power. Remember the distinction between Q target and overall energy gain. While NIF delivered about 2 MJ of laser energy to the target, the laser system itself is incredibly inefficient. To generate those 2 MJ of laser light required drawing something like 300 to 400 megajoules of electrical energy from the grid.
Wait, 400 MJ in to get 3 MJ of fusion out?
Roughly, yes. The wall plug efficiency of the NIF facility is very low, much less than 1%. So while they achieve scientific break-even at the target, the overall facility is still consuming vastly more energy than it produces.
Okay, I see. So the physics works, but the machine is nowhere near efficient enough for power generation.
Precisely. The NIF success has effectively shifted the primary bottleneck for ICF. It's less about proving the fundamental physics is possible. They did that. The problem is now decisively an engineering challenge. It's about developing highly efficient, high repetition rate drivers, lasers or other technologies. It's about inventing scalable, robust, and incredibly low-cost processes for mass-producing near-perfect targets by the millions. And it's about designing reaction chambers that can withstand the blast and radiation from millions of these microexplosions per day, capture the energy efficiently, and breed tritium. The focus has shifted from fundamental science to applied engineering, material science, and manufacturing science.
Okay, so whether it's the patient magnetic approach or the explosive inertial one, achieving fusion isn't just about hitting that triple product. Incredibly difficult engineering challenges remain before any of these approaches might be ready for commercial use. In Part 4, we'll look at the critical hurdles standing between fusion and the power grid and explore some of the other, less conventional paths researchers are taking to get there. We hope you'll join us.
Take care, and we'll see you next time.